Hello students, in this video we'll consider the sine function as a conformal mapping. So let's consider the mapping of the complex plane. By W is equal to the sine of Z. Easy enough, right? Of course, what is this component-wise? We can write this, of course, as what? As e to the I z minus e to the minus I z over 2I, right? That's what it is. So in other words, it's two exponential functions subtracted from each other. So it's not quite as easy to analyze as the other situations we've dealt with before, but let's think about this carefully. When is this mapping conformal? Well, easy enough. Compute the derivative, dw dz is cosine. Okay? And where's the cosine equal to 0? The cosine is equal to 0 at the multiples of pi over 2, right? So I don't want pi over 2. So this is non-zero if z is not equal to 2n plus 1 pi over 2 for n in z, right? Good. So if I look at a region that doesn't include these 2 points, my mapping is going to be conformal, right? So now, of course, the most natural one to look at is just the real part between negative pi over 2 and pi over 2, right? That's where the sine achieves all of its values to negative 1 to 1, right? So let me try to extend that to a strip, okay? So now let's consider the strip. Okay, the half strip, basically. It's really a half strip. It's going to be what? It's going to be, let's call it S. The set points Z, such that what? Such that the real part of Z is between negative pi over 2 and pi over 2. Good. Okay, so in other words, I missed these points where it's not conformal. And imaginary part of Z greater than 0. Okay, that's the region we're going to consider. Let's sketch S, right? So what does S look like? Here is, of course, it's not included. The boundaries are not included, right? I'm just going to draw it like this, though. Okay, that's negative pi over 2. That's pi over 2. Here's the real axis. Here's the imaginary axis. And this is our region over here, right? Okay. So what I want to do is I want to figure out where the sine maps this region. So question, where does sine map S? Okay, good. Okay, so let's figure it out. So here's the idea. The idea is to actually write out what sine is, right? So W is equal to what? Is equal to the sine of Z. If we write Z is equal to x plus IY, this is the sine of x plus IY. That's going to be the what? That's going to be the sine of x, the cosine of IY, and then what? And then plus the cosine of x, the sine of IY, all right? Good. So of course, what's the sine of IY, if you forgot what it is? And sometimes I always forget this one because there's a negative sign issue, right? So let's plug it in. So what's the sine of IY? The sine of IY, so just recall, sine of IY is going to be what? It's going to be a e to the negative y minus e to the y over 2I. And that's the same as I. You can flip the I and make that negative. E to the y minus e to the negative y over 2. So that's just I sinh of y, right? And by similar reasoning, this is just going to be cosh of y, right? Because there's no I in there. So what we have over here is we have our u for our conformal mapping, our u of xy, which W is going to be u plus iv, of course, right? Our u of xy is going to be sine of x cosh of y, and my v of x for this conformal mapping is going to be cosine of x sinh of y, okay? Good. So let's figure out where the boundary curves go. So what happens if the real part of z is equal to pi over 2, right? So if the real part of z is equal to pi over 2, real part of z equal pi over 2, then your u is going to be what? Then your u, if you're pi over 2, this is your u. So the sine of pi over 2 is 1, so you're going to have cosh y, and then that's going to be 0, right? That's what your u is going to be. Sorry, I made them. That's not what u is. U is just cosh y, right? And v is 0. This gets mapped to the curve cosh y 0, right? Okay, what happens when the real part of z is negative pi over 2? So that first curve over there gets mapped to cosh y. This thing over here, you get mapped to where? Well, now what? Now this is negative cosh y. And finally, what happens if the imaginary part of z is equal to 0, and you're between the real part of z is between those 2 points on that bottom face? That's the bottom face. Well, in this case, what curve are you? The imaginary part of z is equal to 0, right? So over here, that means your y is equal to 0, and you just have what? Your y is equal to 0, cosh of 0 is equal to 1, so you're just going to have sine of x, comma what? Comma, again, sinh of 0 is 0, right? 0. Aha! So in other words, what we're doing over here is we're mapping this, the boundary of this region where? So the boundary of the region, if this is 1, this is 2, and this is 3 over here, then what we're doing is we're saying, okay, so here is the real axis, here's the imaginary axis, okay? And of course, where's 1 going? 1 goes over here. So 1 gets to the real line over here. That's where 1 goes. 2 goes between negative 1 and 1. That's where 2 goes. And then 3 goes over here, right? 3. Okay, so in other words, it maps this part of the strip, this half strip, onto the real line, okay? Now, by the fact that it's conformal, we have to prove this formally, but I know that it's going to map the interior, the upper half space and lower half space. We can easily figure that out, right? So for example, I can plug in into this function I, the sine of I is going to be what? It's going to be e to the negative 1 minus e to the 1 over 2i, right? So that's going to be what? The sine of 1, the sine of I, for example, the sine of I is just going to be I times the sinh of 1. I times the sinh of 1's over here. So if I plug in I, that gets just mapped to what? I sinh of 1 goes right over here. I sinh of 1. Beautiful. So now it's going to go upper half space. Let's do some more analysis of this though, right? So let's suppose real part of z in this region is equal to a constant. Then your u is what? Then your u is going to be the sine of a constant, sine of c1 cosh y. And v is going to be what? V is going to be cosine of c1 sinh y, right? Good. And therefore what? And therefore u squared over sine squared c1 minus v squared over c1, or cosine squared c1, right? That's cosh squared minus sinh squared, that's equal to 1, so this is a hyperbola. With foci, you have to add the denominators, right? With foci at plus minus 1, okay? So these lines real gets mapped to hyperbola over here. Over here, you get mapped over here. And their foci are here and here. What happens if the imaginary part of z is constant? Suppose imaginary part of z is constant. Suppose imaginary part of z is a constant c2. Then what do you have? Then you have your u is going to be what? Your u is going to be cosh c2 sine x. V is going to be sinh c2 cosine x, okay? And these are ellipses, right? Sine, cosine, these are different numbers over here. So these are ellipses with foci. You have to subtract those two things to the foci plus minus 1. Beautiful, right? Ellipses with foci plus minus 1, right? So in other words, those maps go like this. The imaginary part of z constant, like this, give you what? Give you ellipses like this. And these things are perpendicular to each other by conformality, right? So in other words, you're getting all of these hyperbolas like that. And that tells us, of course, that's the conformal structure, right? We can see that the way I've drawn this looks like, oh my gosh, wherever they intersect, they're perpendicular to each other. In some sense, what's happening over there is this is a good illustration of the fact that these conformal maps have lots of good structural properties to each other, right? So these angles over here, we want to show that these conformal mappings over here, in some sense, preserve the Laplacian up to a scaling factor, okay? And so that's exactly what's going to save us here. So beautiful, beautiful result. So the sine is doing what? The sine mapping is taking this half strip, it's mapping it to the upper half space, and the level sets are being mapped to hyperbolas and ellipses, and all those hyperbolas and ellipses are confocal. They have the same foci, right? So they're confocal ellipses and confocal hyperbolae, right? So in other words, the sine map is really unlocking a really beautiful geometry here. In other words, this is sometimes called like elliptic hyperbolic geometry in this case. And so we're really going to have to see if we can dive deeper into this field to try to make sense of what these configurations mean, but they give you a lot of information and make your computations in the study of harmonic function theory very simple, right? So in other words, this is the preferred state, and so understanding these functions, these very simple elementary holomorphic functions as conformal maps gives us good intuition for how to solve particular boundary value problems where there are different geometries involved. Thank you very much.